So the second experiment in our Swansea Analyst contest for this year is all about aspirin analysis by spectroscopy. The actual experimental part of this is dead easy. It's the calculation part that can take some time, and also it's worth spending a little bit of time introducing the background for it. Anyway, what we're going to be doing is we're going to be looking at a coloured substance. Why are things coloured? It's because they absorb particular wavelengths of visible light and allow other wavelengths to pass through or to be transmitted. The more intensely coloured things absorb more light, and the way we say that in a fancy fashion is we say they've got a higher absorbance, A, they absorb more light. And for dilute solutions, the absorbance A is directly related to the concentration, it's proportional to the concentration as described in Beer's law. A, that's the absorbance, is equal to epsilon L. Now these are just constants that are associated with a particular substance, that's the epsilon, and L is how much of the substance, the path length you had there. So these are going to be a constant throughout our experiment, okay? And then here's C, the concentration. So you can see A, absorbance, is equal to a constant times the concentration. And that's so important, absorbance directly proportional to the concentration. I think I've said that one way or another 5 times. This Beer's law is the fundamental idea that we're going to be utilizing in this experiment. So we can determine the concentration of a coloured substance if we can measure the absorbance of that solution and we know the values of epsilon L. And to do that, we use an instrument called a spectrophotometer. Spectrophotometer shines light through a sample of different wavelengths of light and compares the intensity of the light after it's gone through the sample with the intensity before. Okay, and we can study these coloured compounds by determining how much light is absorbed by known concentrations. So if we measure the absorbance and we know the concentrations, now we can determine epsilon L. And then once we know epsilon L, we can measure the absorbance of an unknown sample to determine the concentration. And that in a nutshell is what we're going to do today. If you're in the lab, you would see our spectrophotometer. It's a nice diddy little thing there. We put our sample in a square test tube called a cuvette into that hole there, and then we beam light through it. So the light goes in there through the sample. We measure what comes out afterwards, and then we'll display the results on our computer screen. So here is a sample in the cuvette, and you can see it's lit up because the light is passing through there. And again, light passes through, some of it's absorbed, the rest is transmitted. Knowing what goes in, measuring what comes out, enables the computer to plot out the absorbance, and we'll get something like this. Okay, along the bottom there is wavelength of the different types of visible light. We got this pretty little background that shows you that the shorter wavelength or the higher energy visible light is purple, and then of course you get that famous little sequence going through violet or purple, then blue, and then green, then yellow, then orange, and then red. And this of course is the longer wavelength or the lower energy of the visible spectrum. Absorbance up here. So what we see is that the sample isn't absorbing much of the red, absorbs a little bit in the higher wavelengths red, a little bit of the orange, peaks in the green spectrum, okay, and then goes back down, isn't absorbing as much here, absorbs a little bit up in the purple as well. So this is the absorption spectrum of whatever my sample is in here, and the computer prints out, I didn't put everything on there, but essentially these are the absorbance heights that match up to the particular wavelengths that's off the screen there. So this is the spectrophotometer we're going to use, and this is the kind of output that we get. Now in this particular lab, we're going to measure the concentrations of ferric salicylate. Try saying that 5 times quickly, which is a lovely purple color. So what we're going to do, take different concentrations of that, measure the absorbance, and we'll use Beer's law, measuring the absorbance for the known concentrations. We can calculate epsilon L. Okay, then we're going to take an unknown solution of the ferric salicylate, measure its absorbance, and thus determine its concentration, because if we know epsilon L, measure A, we can calculate C. Now this is a particularly useful little process because it's actually used to test for aspirin. Okay, ferric salicylate of interest for a test for aspirin. Let's actually look at the chemistry associated with this. I'm going to start with the compound salicylic acid. That's what we're going to use in the lab. We're going to measure out a certain amount of salicylic acid. We're going to put it in solution. We're going to react it with sodium hydroxide to make this compound sodium salicylate. So you can see all that's happened is the Na has replaced the H there. Now, if we take sodium salicylate and we react it up with Fe3+, we make this beautiful purple compound here, ferric salicylate or iron 3 salicylate, in which there's the Fe3+, and it's reacted with 3 of these formerly salicylic acid moieties. Essentially, the Fe3+ has replaced the Na+ on 3 of these. Okay, so this is the reaction we'd actually do in the first part. We take known amounts of salicylic acid, react it up with sodium hydroxide to get known amounts of sodium salicylate, which we then turn into this pretty purple compound to do the analysis. Now, I said that was something to do with aspirin, didn't I? Well, this is aspirin here. It is salicylic acid. There's the benzene ring with the acid group, but instead of an OH there, instead of that so-called phenol group, if you know that, we've put on this acetyl group here. Okay, so acetyl salicylic acid, this compound here is aspirin, give you the molar mass as well. Well, if we take aspirin and we dissolve it up in a solution of sodium hydroxide, the aspirin converts to the sodium salicylate again. In other words, you break off this group here and replace it effectively with the H, and we replace the H on this acid group with the Na. And so we take aspirin, we turn it into sodium salicylate, we convert that to the ferric salicylate, and we can determine the concentration of the sodium salicylate and hence the amount of aspirin, very much similar to what we did if we just started with salicylic acid. So we're going to use salicylic acid to develop all our known values, our epsilon L, and then we're going to take some unknown aspirin, going again through sodium salicylate to determine how much aspirin we have in there. Hopefully that vaguely made sense. As we go through, anything that's unclear might become clearer if we're lucky. So, first part, I'm going to take known concentrations of sodium salicylate made from salicylic acid, reacting with Fe3+, and then we're going to make the aspirin solution from a tablet, measure its absorbance, get the concentration of the sodium salicylate, and hence the mass of the aspirin.